Hi guys, so today we're going to look at how to find the inverse of a matrix, and then we're going to look at how to use that to solve a system of equations. So first of all, when it comes to inverses, in order to tell if two matrices are inverses of each other, there are two things we need to consider. One is that A times A inverse and A inverse times A. So remember, when it comes to multiplying matrices, order does matter. It's not commutative. Those can actually be two different equations. Now, both of those products have to equal the identity matrix. And if you remember the identity matrix from earlier, the identity matrix was one for a 2 by 2, where you had the ones on the diagonal, and for a 3 by 3, you also had the ones on the diagonal. Now, when it comes to finding the inverse of a matrix, only a square matrix can have an inverse because it's based off of the determinant, but not every square matrix will have an inverse actually. So let's look at this first example. We're just going to determine if these matrices are inverses. And what we're going to do is we'll do A times A inverse and A inverse times A. Figure out if both of those equal the identity. So to start, we'll do A times A inverse. So I'm going to go row by column. So negative 2/3 plus 5/3. Then I'm going to go row 1, column 2. So 5/12 minus 5/12. Then I'm going to go row, column, negative 8/3 plus 8/3. And then finally, I'm going to end with bottom row, last column. That gives me 20/12 minus 8/12. I can simplify. I get 3/3, 0, 0, 12/12, which is the identity matrix. So now I'm going to try the opposite way. So I'm going to go A inverse times A. So I'm going to go ahead and rewrite A, just because I think it's a little easier to see them in the correct order. All right, and again, I'm going to start row, column. So that's going to be negative 2/3 plus 20/12. Then I'm going to go row 1, column 2. So negative 10/3, 40/12. Row 2, column 1, 1/3 minus 4/12. And finally, bottom row, last column, 5/3 minus 8/12. So when I simplify, that's going to be 12/12, which is just 1. That's going to be 0, 0, and 12/12, which would just be 1. So both of those products gave me that identity. So yes, those two matrices are inverses of each other. All right, so now looking at B, we'll try the same thing. So first row, first column, that gives me 1/2 plus 0 plus 1/2, which is 1, which is what we want in that top corner. So first row, second column, 1/2 plus 0 minus 1/2, which will give us 0, which is what we want in that spot. So first row, last column, negative 1/2 plus 0 plus negative 1/2. So that's going to give me a negative 1, which is not part of the identity matrix. So at that point, we know that those are not inverses of each other. All right, so instead of just proving whether or not these are, we're going to look at how to actually find the inverse. So in order to find the inverse of a matrix, what we're going to have to do is use the determinant, and then we're going to use a different form of that matrix. So what we'll do first is we'll find the determinant of the matrix. So on A here, let's go ahead and find our determinant. So that's going to be 4 minus 6, which is negative 2. So the determinant of that matrix is negative 2. What I do to find the inverse is I take 1 divided by the determinant, and I multiply it by a different form of that matrix. What I do is I flip that top diagonal, so A and D, those two are going to switch places, and then I change the signs of the other two. So A and D get flipped, so that becomes 1 and 4, it becomes negative 2 and negative 3. Then I can multiply those by that scalar, by the negative 1/2. So negative 1/2, 1, 3/2, negative 2. So that's the inverse of that matrix. All right, so let's go ahead and look at B. So again, same first step. I would start by finding the determinant. So 4 times 1/4 is 1, minus 3 times negative 1/3 is 1. 1 minus 1 is 0. Well, the problem here, if I try and find my inverse, I would do 1 divided by the determinant. 1 divided by 0, I can't do. So this is a case where there is no inverse. So this matrix does not have an inverse. So if the determinant is 0, then we are not going to have an inverse of that matrix. All right, so now we're going to look at how this relates to systems. And this is what's going to be really helpful for us. So what I'm going to do in order to solve this system using matrices, I am going to rewrite this system using matrices. So I'm going to write the coefficient matrix. So this is going to be 1, 1, 2, 1. Well, then to keep this whole system as matrices, that system, the x plus y and the 2x plus y, that would be the same thing as that matrix times xy. Because if I went back and did my operations, well, I would do 1 times x plus 1 times y. That would give me x plus y. And then if I went to the bottom row, 2 times x plus 1 times y, that would give me my second equation. So this matrix here, this multiplication of these matrices, is the same as what I have over here. So as an equation, this is going to equal the matrix 8, 1 that's on the other side. So to figure out how we're going to solve this, what I'm going to do is I'm going to call this one A, I'm going to call this one X, I'm going to call this one B. So A is going to be my coefficient matrix, X is the variable matrix, and B is the constant matrix. So in order to actually solve this, what I could do, you can't really do division with matrices, but what we can do is we can multiply by the inverse. So right now I have A times X is equal to B, and I'm trying to get X by itself. So what I can do instead is I can multiply both sides by A inverse. Now notice over here on the right side, it's A inverse times B. It's not B times A inverse. Because again, A inverse times B actually exists as a solution, because it would be a 2 by 2 times a 2 by 1. The other way around, it wouldn't actually work. Now when I do this, A inverse times A, well, that's just the identity matrix. So I'm left with that variable matrix is going to equal A inverse times B. So to solve a system of equations, all I would do is A inverse times B. So let's go ahead and find A inverse. All right, so to find A inverse, I'm going to need the determinant of A. So that's going to be 1 minus 2, which is negative 1. So once I know the determinant, A inverse is going to be 1 over the determinant. And then I flip the down diagonal. I change the signs of the up diagonal. I'm going to go ahead and multiply by that scalar. So the inverse is negative 1, 2, positive 1, negative 1. Once I know the inverse, in order to solve, I'm going to do A inverse times B. So I'm going to do negative 1, 2, 1, negative 1 times 8, 1. So again, I would do to multiply row by column. So that's going to give me negative 8 plus 1. Then I'm going to do again row by column. That's going to give me 16 minus 1. And if that matrix is equal to xy, it's easy to see now that x is equal to negative 7 and y is equal to 15. All right, so that's another way that we can use matrices to solve systems. So let's go ahead and try another example. Go ahead, pause the video, and then try to solve this one using matrices. All right, so what I would do here, I would start with my coefficient matrix. So that's A. So I'm going to find A inverse. Start by finding the determinant. So that's going to be negative 6 minus 25, which is negative 31. Once I know the determinant, the inverse is going to be 1 over the determinant. I take the coefficient matrix, switch places, change signs, multiply by that scalar, and there is A inverse. To actually solve this system, it's A inverse times B. So there's A inverse, there's B, and then we'll actually multiply it. So top row by that first column, so 0 plus 5 over 31 times 31, just 5. Then I'm going to go bottom row times that column, so that's going to be 0, and then it's going to be negative 2 over 31 times 31, which is negative 2. So x equals 5, and y equals negative 2. Now what's really nice about this, right now it might not seem like it's that much of an easier solution than the methods you guys have used before, but going forward what's really going to be helpful for us, this is going to be a very fast way to check our 3x3 equations, and also a really good way to find solutions to some of those messy 3x3 equations. So let's go ahead and look at a 3-variable system. So we're going to solve this using inverse matrices. But to find the inverse here, we're actually going to use the calculator, because finding the inverse of a 3x3 matrix, it's going to take a lot of extra time, a lot of extra calculations. We're just going to use the calculator to actually find our inverse here. I'm still going to solve it the same way though. So I'm still going to do A inverse times B. In order to do that, I need to know what A is. So A is the coefficient matrix. So 3, 2, negative 2. 2, negative 1, 1, negative 1, 3, negative 7. So that's A inverse. So I'm going to do A raised to the negative 1 power times B. B is going to be 3, 2, 1, and that's going to equal X, Y, Z. So what I'm going to do is I'm going to go ahead and actually just put all of this straight into the calculator exactly the way it's written, and that's going to solve my system for us. So let me go ahead and pull up the calculator. All right, so you can either enter this matrix by going to that MAT and actually storing it, or if you'd prefer instead, we can just go to Math and then MAT, and we're going to do our 3x3. So I'm going to type in the values of my coefficient matrix. All right, so I plugged in my coefficient matrix. I'm going to raise that to the negative first power, because that's my inverse. I'm going to multiply that by a 3x1. And then that 3x1 is going to be 3, 2, 1, because that was what was on the other side of the answer column. And then all three of these are going to be my solutions. So the first one on there, the 43 over 28, that's my x. The negative 33 over 28, that's my y. And the negative 3/4 is my z. So x is equal to 43 over 28. Y is equal to negative 33 over 28. And z is equal to negative 3/4. So this gives us a really fast way to check some of these values for those 3-variable systems. It also really helps getting some of these kind of ugly numbers that we really wouldn't want to work out if we were solving this system by hand. All right, so the last thing we're going to look at is just an application. So what we're going to look at here is something where you have an encoding matrix, and that matrix was multiplied by a message basically to create something that's in a code. So what we don't know is the original message. What it says happened is we took the encoding message, we multiplied it by our actual message, and that created this C equation. So in order to actually figure out what that message is, I'm going to solve this a very similar way that I just did. I'm going to need to multiply by an inverse. So if I multiply by E inverse, well then I'm going to be left with just what M equals. And the message is going to equal E inverse times C. So what I need to do to solve this is actually find E inverse. So if you want to find this from the calculator, since we're doing a little more of an application question, that's okay. But I'm just going to review how we found that. So that would be the determinant of E first. So 6 minus 49. Then I would do 1. So E inverse would equal 1 over the determinant times, switch places, switch signs. Actually multiply it out. And there's my encoding matrix. So then what I would do to actually solve this, I'm doing E inverse times C. So I'm going to take that inverse and I'm going to multiply that by the C that I was given. And I'm going to go ahead and use a calculator for this just because it's going to take a little bit too long with some of these fractions to actually find those values. But go ahead and plug this into a calculator and see what you get as a result. All right, so when I go ahead and plug that into my calculator, so what I plugged in there, that -6 over 43, that was A inverse. I multiplied it by B, and then this result here is basically my code. Every number on there stands for a letter. So A equals 1, B equals 2, C equals 3, etc. So that matrix, we can replace each of those numbers with a letter. So like this would be A, this would be B, the zeros would be spaces, this would be E, and then you can go ahead and finish that up to see what that would read. All right, so again, that's just an application of using these matrices. So we will look at the last method for solving systems with matrices next week.